The universe is a vast and wondrous place, isn't it? For centuries, we humans have gazed at the stars and pondered the very nature of reality. During the early part of the 20th century, two revolutionary theories emerged that completely changed our understanding of the universe. The first was Albert Einstein's theory of relativity. It painted a new picture of space, time, gravity, and the cosmos at large scales, the world of planets, stars, and galaxies, and things moving at incredible speeds. Then came quantum mechanics, a bizarre and wonderful description of the universe at the smallest scales, the realm of atoms and their constituents. These two grand theories, relativity and quantum mechanics, didn't initially sit comfortably together. That deeper theory, the magnificent synthesis that managed to weave together the principles of quantum mechanics with Einstein's special relativity, is known as quantum field theory, or QFT. So, how should we picture this universe described by quantum field theory? Forget the old idea of tiny, hard billiard balls whizzing around in an empty void. Instead, imagine the universe as being filled, utterly permeated by invisible entities called fields. These fields are not just mathematical constructs. According to QFT, they are the fundamental reality. What exactly are these fields? They are fundamental entities, each with its own unique properties. There's an electron field, a quark field, an electromagnetic field, and so on. Particles, as we observe them, are not tiny, indivisible points. Instead, they are manifestations of these underlying fields. They are like tiny ripples or vibrations or excitations in their respective fields. This dynamic interplay between fields and their particle excitations is what QFT describes so successfully, painting a picture of a constantly shimmering, energetic cosmos. Let's explore these cosmic fields a bit more. A key feature, inherited from quantum mechanics, is that these fields are quantized. This means that when a field vibrates, it can't just have any amount of energy. The energy in these field vibrations comes in discrete packets or bundles called quanta. Each quantum is the smallest possible unit of excitation for that particular field. Now, where does Einstein's special relativity fit into this picture? Special relativity, as you might recall, is built on two main postulates. QFT was designed from the outset to be fully compatible with these principles. This successful marriage of quantum mechanics and special relativity is what makes QFT so powerful. So we have these fields and we have their particle excitations. But how do these particles talk to each other? How do they exert forces on one another? How does an electron, for example, know that another electron is nearby, causing it to be repelled? QFT offers a wonderfully intuitive yet deeply profound explanation for the fundamental forces of nature, like electromagnetism or the nuclear forces. Imagine two children on roller skates facing each other. If one child throws a heavy ball to the other, the act of throwing will push the first child backward. When the second child catches the ball, they too will be pushed backward. The net effect is that the two children move away from each other as if a repulsive force acted between them. In the world of QFT, fundamental particles interact by exchanging other specific particles known as force-carrying particles or messenger particles. This particle exchange model applies to other fundamental forces too. So, every interaction you see, from the light of a distant star reaching your eye to the intricate dance of particles in a nuclear reactor, is underpinned by this constant subatomic game of catch. Section 5. The whispers of nothingness, the lively quantum vacuum. What about empty space? If these quantum fields permeate everything, is there such a thing as truly empty space, a perfect vacuum? Quantum field theory gives us a rather startling answer: no. Even in the most profound void, far from any matter or radiation, the quantum fields are still there, and they are not quiescent. The vacuum, according to quantum field theory, is a seething, bubbling cauldron of activity. It's a place where the fields are constantly undergoing tiny, random fluctuations. Out of these incessant energy fluctuations in the vacuum, something remarkable can happen. Pairs of particles and their antimatter counterparts can spontaneously pop into existence, exist for an incredibly brief moment, and then annihilate each other, disappearing back into the fluctuating field. Despite their fleeting, virtual nature, these particles are not just a mathematical fiction. The vacuum, it turns out, is a dynamic and influential part of our universe. Section 6. Taming the Infinite. The clever art of renormalization. When physicists first started to explore the mathematical consequences of quantum field theory in detail, they encountered a significant hurdle. When they tried to calculate certain physical quantities, such as the mass or charge of an electron, their equations often spat out an answer that was infinite. This was, to put it mildly, a bit of a problem. The solution came in the form of a sophisticated set of mathematical procedures known as renormalization. Renormalization provides a systematic way to handle the infinities by absorbing them into a redefinition of a small number of these physical parameters. This procedure, while mathematically complex, has proven to be astonishingly successful, allowing QFT to make incredibly precise predictions that match experimental results. Section 7, the Standard Model, our best yet incomplete map of reality. The decades of development and refinement of quantum field theory have culminated in what is arguably one of the most successful scientific theories ever constructed, the Standard Model of particle physics. This model is a specific QFT that describes all the known fundamental particles and how they interact via 3 of the 4 fundamental forces of nature. The Standard Model neatly categorizes the fundamental constituents of matter into 2 main groups, quarks and leptons. One of the crowning achievements within the Standard Model framework was the theoretical prediction and subsequent experimental discovery of the Higgs boson. However, despite its incredible successes, the Standard Model is not a complete theory of everything. It has its limitations and leaves some profound questions unanswered. So, while it's our best map so far, there are clearly uncharted territories beyond its borders. Section 8. The Unseen Architect. Why Quantum Fields Matter to Everyone. You might be sitting there thinking, this is all very fascinating, but what does quantum field theory with its invisible fields and virtual particles have to do with my everyday life? It's a fair question. Many of the technologies that we rely on in the 21st century are direct or indirect consequences of our understanding of quantum mechanics, for which QFT provides the most complete and robust framework. The lasers that read your Blu-ray discs or are used in delicate surgeries, the transistors that are the heart of every computer, smartphone and digital device, all operate on quantum principles. Medical imaging techniques like positron emission tomography, PET scans, rely on the physics of antimatter annihilation, a concept deeply embedded in QFT. Beyond the practical applications, QFT profoundly shapes our worldview. Ultimately, learning about quantum field theory, even at a conceptual level, allows us to glimpse the very architecture of reality. It's a story of human ingenuity, our relentless drive to explore and understand. And it offers a profound sense of connection to the intricate hidden symphony that plays out all around us and indeed within every atom of our being. Section 9, the next movement, the enduring quest for understanding. Quantum field theory, then, stands as a towering intellectual edifice, providing us with our most profound insights into the fundamental nature of particles and their interactions. It has successfully unified quantum mechanics with special relativity, described the dance of matter and forces with incredible precision through the Standard Model, and even given us a peek into the strange, energetic nature of the vacuum. But the symphony of the universe is vast, and QFT, for all its power, has not yet revealed all of its movements. The most glaring omission from the Standard Model, and thus from our current successful applications of QFT, is the force of gravity. Several ambitious theoretical frameworks are being explored as potential candidates for a quantum theory of gravity and perhaps a more complete theory of everything. The journey to comprehend the universe at its deepest level is far from over. The hidden symphony of the universe continues to unfold, and we remain eager listeners anticipating the next, perhaps even more astonishing revelations.